Welcome everybody to another episode of Rudy's Electronics Lab, and today I want to pay some more attention to the Rohde and Schwarz SMIQ RF generator. And you might have seen it being used as a workhorse in my videos already quite a few times, but I haven't really made a lot of dedicated videos on it. And it is already like almost 25 years old, but I do think it can do pretty special things or so. And today I'm going to look at its functionality as a arbitrary waveform generator. And you might say there are a lot of arbitrary waveform generators out there, and I covered some, much more affordable models, etc. Even recently. But there's very special things I think that this model can do. And even if you were given some, say, 10,000 euros right now, and you would have to buy a brand new signal generator, RF signal generator, I think you'll be hard pressed to find something that could do similar things as that we're going to look at today. So what type of things I'm talking about that will be not so easy to do? For example, to create proper signals according standards like GSM or 3G or GPS, create real vector and IQ type of signals without additional equipment, but also things like creating a multi-carrier signal of say 30 carriers, then maybe leave some specific carriers out because there's going to be interference at those frequencies, modulate all these carriers with a different content, add in some IQ impairments, phase noise, add some band pass, some amplifier distortion to it, power ramping, then add a couple of multi-pass type of reflections that you define, and then finally also add noise to it according to some specified type of parameters. Now all of this stuff you can do, and I'm actually going to go deeper into the ARB functionality of the device today. And I think by every sense, you feel in every way this is a very professional instrument. The build quality, I think it's like 26 kilos. No, not that in itself is a feature, but its build quality is impressive. The documentation is great. There's great documentation on the device itself, but today we're going to specifically look at the ARB side, and we're going to look at the software needed for that. And even for that there is like a 600-page manual for the software alone that even reads like a whole 101 course on telecommunications or so. So it's amazing, how well this is all documented, even though there's some gaps in the documentations, as we will run into in this video. So this video is going to be of two parts. First, after a brief introduction of the device, we actually go to some experiments and we're going to see it working. And then in the second part, I want to talk about all the specific things that I did and tried before I got it working, because that is not so obvious, because being almost 25 years old, you really have to create for the software a computer environment that looks like it was 25 years ago, both in all the operating system, the hardware interface, the additional software. So I'm also making this part, adding this as the second part of the video, basically for anyone that would like to try to do the same thing to prevent that you have to invent the wheel again. But first a short introduction, and I'll go to some measurements of the device. So let me give a short description of the device. This is not a whole review, but to put it all into context, this device can do a lot of different type of modes. You have regular type of analog modulation with external inputs and everything. You have vector modulation, so complex type of signals using basically a external input signals for the I and Q if you generate them from somewhere else. You got built-in digital modulation for all types of modulation parameters like amplitude key shifting, we got phase, we got frequency key shifting, we got QAM type of things up to 256 QAM, and nicely all right out of the box. So you don't need any additional software, you just turn it on, you select it, you select the parameters, and it works. I made another video where I go much deeper into that. You got all type of digital standards, at least for that period, modern digital standards being implemented in the device, creating like compliant type of waveform, 2G, 3G, GPS, much more. And we got a arbitrary waveform functionality, and that's what I'm going to be focused on today. And that's where we need a piece of software, and that piece of software is called WinIQSIM. And much of the video today is going to be about how we can use that software basically to work with this machine. Apart from From what I just said, I mean, the device is interesting because it really has a lot of inputs and outputs. You see a number of them listed here on the screen right now. They're on the back of the device as separate connectors. Some of them are together on like some very large D sub type of connectors. But there's so much in and output for triggering, for syncing frames or whatever, etc. If you really want to do advanced stuff, and in some of the other videos I've been using that, it's there. There's also bit error ratio testing in here. I'm probably going to do a new video on that as well. And there's interfaces, and we'll go a little bit into, we got the GBIP interface, and we also got a serial interface. Now, focusing now on the arbitrary generator, a lot of the things already shown, it all depends basically on the software that you, and the software options and the hardware options that you got in the machine. If you want to do the arbitrary generator, you need the B11 hardware for the device and the B60 software option there. And what you're getting there basically is a true IQ generator, and that really sets it apart from many arbitrary devices on the market, really a IQ generator. If we look at the memory, we got 15 megabit wave memory as a standard built into the device, and you can add up to 2 additional memory modules, and each of them is 32 megabit. Now, on this table here, you see a little bit how that memory works, and you have to take care a little bit how exactly that is implemented, because it's in megabit. So we could translate to megabytes, you could compare it more to computers. But if we talk about this type of arbitrary waveform generator, generally we're working in words of 16 bits, so we have to divide it again by 2. And if we make an IQ signal, of course, we need 2 samples per single symbol period or so. So you have to divide it again by 2. So in this table I'm kind of showing you what we have left at some point. Now about the memory, there's also some interesting note that we find in the documentation of the device, and that says that you cannot really compare the amount of memory in this device with what Rohde and Schwarz calls a conventional arbitrary generator. And the point that they're kind of making is that they have like a hardware interpolation in the device that basically prevents you from having to do large degrees of oversampling, and that this would actually compare to another device that has like kind of 3 or 4 times as much memory. I'm just giving you this information for what it is. I will show in a video that even with a very limited number of samples, etc., we can already do quite interesting things. But anyway, this device right over here, it has one of these additional memory modules installed in it right now. We got a sample rate of 40 megahertz. The resolution is 12 bits. There are these days devices that go 14 bits or even higher, although not necessarily with great speed. The memory that we have is non-volatile. That's interesting. So if I create a waveform, and I created a couple of this week, and now if I turn it on this morning, all the waveforms are still there. That's really interesting, also given it's quite a job to get the waveforms there, as you will see. There's extensive marketing, triggering going on, etc. And then of course an RF generator, so we can modulate the signal in this version all the way up to 3 gigahertz. There are other versions of the SMIQ that go all the way to 6 megahertz. Now over here you see a little bit how the internal architecture of the device works, where we got basically the modulator on the right, where we see the several options of kind of built-in waveform generators, and the part that the video is focusing on today is basically the part on the left, what is shown here in yellow, and that is really the data generator, and there's also the memory modules, the built-in memory and the additional memory that you can pay back from. But as you see here on the chart, basically it's also the possibilities to have external digital signals coming in, external analog signals coming in, and do all this vector modulation that I already talked a little bit about. Now, I think that's enough for now. Let's basically go to do some experiments and see how it works. Now let's go and do some measurements, and I got my SMIQ here, I got the Windows XT computer connected here, and I connected up an oscilloscope, and the oscilloscope is currently looking at the I and the Q channel, and also looking at the modulated RF signal, which is of much higher frequency, as we can see here. And we see there's already a waveform being sent out right now. It's a complex IQ type of waveform that I earlier loaded into my SMIQ, and we can see here it's a 184,000 sample waveform. It actually took like 5 minutes or so, I think, to transfer it via the serial interface to the device, but it worked in the end. Having this complex waveform, of course, we could also be looking at the vector properties, and then we basically see that this waveform, it's all modulated around the same amplitude. So we get a circle here, and we can go into the spectral domain. So what we actually see here, that, and now we're seeing channel 4 of the scope, that's the modulated signal. So it's modulated at 100 megahertz with 0 dBm level, and we see this complex signal here at being present here at 1 megahertz here. Okay, this is the starting point for our experiment. I already loaded this in advance, but now we're actually going to see to create some new waveform using the IQ generation program of Rohde and Schwarz. The important thing is that we first got the port settings right here. So these are the port settings I'm using. I think this is the highest speed that seems to work reliable, and I got the same port settings there in the SMIQ. I'll not go there right now, and let's go and take a look at the actual software running. So this is our software package. This is normally how we start like. So we have a block diagram here which has all the different parts here from the data source typically. Well, let me move it by the way first. First you choose basically a type of signal that you're starting with. So you could do a single carrier, you can do multi-carrier type of signals, you can do stuff related to various type of standards, or import your own signal. And depending on what you choose here, this block diagram is going to differ. So I'm going to choose here the single carrier. I'm going to get the block diagram for the single carrier, and everything activated is in green. So we see the data source here, and the data source, for example, is now a pseudo-random bit sequence of 9. But we can also basically go to a data editor where I can have a complete slot type of structure here. And we can actually have our own files by which we fill out the device with data here. Now I'm just going to leave it right here. We got the modulation setting. Let me just move this one around a little bit. And in the modulation setting, we basically choose the way that the signal is being modulated. So we got all the type of phase and frequency shifting. We got QAM up to 256. We got user type of modulation settings that can be programmed into the device. We can actually decide how this is being, the data is going to be coded into positions in the modulation scheme here, depending on what we have chosen. We got a simple rate, we got the length of the sequence, we got filter functions, and if this is not even advanced for you, you can also see here information about the constellation that is being generated. So pretty advanced, would say. Now we only looked at the modulation setting. We got the IQ impairments, in which we can make deliberate type of errors into the IQ signals. We can distort the phase of the signal that we're working with. We can add bandpass type of filters here, can turn them on and off. We can have amplifier distortion effects. We can have power ramping. We have multipath effects here, so we can define several kind of reflection paths where a signal comes in a delayed and possibly weaker version back into the signal. We can do stuff with offsets in the phase and the frequency domain, and then this is created like the useful signal, and up to that we can have an interference signal, like a noise signal coming on top of that. So we can define the type of noise that is kind of coming in the interferer, and several of other things. Now the wanted signal and the unwanted signals are basically added up, go through a receiver filter, quantization. Let's take a look. We can do the IQ quantization here, and basically get that here, and here we can decide whether the IQ generator is on and off. And this is basically for the single carrier signal. So if we go to basically another type of signal, so that takes the 3GPP 3G wideband CRMA standard here, we're going to get like basically another type of block diagram. So let me move the windows a little bit around so we can all see them. So we basically, well, now we still roughly got the same things here. Here we see later that we could have other things as well, but here we see 3DPP configuration parameters according to that standard. We see constellation diagrams and other types of things here. Now today I will be basically focusing, let's take a look at one more. Let's look at the IEEE protocol. Oh yeah, okay, here you see we get again, our block diagram, but here we get basically the slot structure of a Wi-Fi signal. So plenty of possibilities to start off with, but I want to go and create a multi-carrier signal because that's the type of signal that will be nice to inspect on the oscilloscope. So we go there, and actually now we see that the block diagram is slightly different. Some of the things are the same here, but we got multiple carriers that can be programmed right over here. And that's actually what I'm going to do now. So I'm going to go to the multi-carrier settings. Here I can define a number of carriers. So let me say that the system creates 40 carriers now. And now on this list here, let me just bring it here next to it. I got basically 40 carriers I can choose from. I can turn individual carriers on and off. I can decide their power, whether they're going to be modulated, and if modulated, with what type of signal. I'm not going to do any modulation now. I'm going to turn on the constant wave mode here, and they're spaced 1 megahertz apart, each of these signals. So I'm just going to turn a selective number of channels on here so we can easily inspect it. So I'm going to turn on number 19, and then I'm going to take a couple of notes, and then 23 and 24, and I'm going to pause again, 3 of them, and then I'm going to take 28, 29 and 30. So that basically means that I should have like a visible type of spectral diagram with 1 carrier, 2 carriers a little bit further on, and 3 carriers. And actually we can look in the domain here. It's in red here. We already see the carriers that's supposed to be there. I can also say over here that I can put 30 carriers already directly on, and then carrier 10 to 12 I can turn off here. So there are quicker ways of doing this basically, but I just did it manually. So this is basically the carrier wave that I decided upon. I can do also some oversampling, but I have to take care a little bit. I'm now into a fairly small sample, only 316 samples. So we have to see actually what we get to see with so little samples. But we are already here at the 40 megahertz sample frequency. So if I would turn on oversampling here, I would actually go to about 80 megahertz, but that is more than the SMIQ will support. So then I'll have to go to another spacing if I would like to do something like that. So I'm sticking here basically at the spacing at the oversampling of 1, having slightly less than 40 megahertz. I come back to that in a second, and that still fits here. So despite a very small sample, let's see if we get some useful type of signals out of the device. And remember, by choosing another carrier spacing, of course, I can get a much longer signal in signals. It will be just modulated slightly differently. So I'm going to say OK here. And then the next step I probably want to do is kind of inspect how that signal would look like if we compute it internally into the system. So I can go to graphic settings. I can first inspect here the time domain property, and I can graph it. Yeah, and this will be basically the time domain signal that we created. Was a complex signal because we activated 5, 6 carriers in total. But it might be more interesting to look at in the frequency domain. So I'm going to look at the FFT magnitude. I'm going to choose an automatic number of FFT points here, plot the graph, and here we go. So we already see calculated exactly what we've been predicting: a carrier, 2 carriers and 3 carriers, and that's what we should be seeing back at some point at the oscilloscope there. Now let's try to go and send this signal over to the SMIQ. So I already selected the SMIQ here. Actually, if I go to target the type of waveform generator I'm using, I'm being told here about the minimum clock rate, 1 megahertz, the maximum clock rate, 40 megahertz, already mentioned before, and the maximum sample length, which is 500,000 samples here. I believe this is actually if you have the device with the standard memory, not the extended memory. I think I have 3 times as much memory because I have option B12 installed here. But anyway, we're seeing something of a maximum here. So I got the right generator being there. There are a couple of other settings basically here in terms of the transmission options. So yeah, this is a bit confusing. I've several times changed it, but it's more important that actually the underlying hardware interface is configured properly. So I'm going to try to send over this waveform here. So I'm going to go to the transmission protocol here. I got to give it a name. Then he's starting something that I actually don't want to start, but that's no problem there. And I'm going to call it MC 1, 2, 3, multi-carrier 1, 2, 3, and actually I already wrote this text before, multi-carrier 1, 2, 3 with 1 megahertz spacing. So there's also an IQ swap possibility. The whole thing of IQ is not defined in the same way over different type of telecom protocols, whether you add the I in the Q or where you subtract the Q from the I, like for example the IS-95 standard from the US does, is a bit of an exception. We don't need that right now. So let's go and transmit it over to the device. And that's already it. He's already been sending it over, so let's move to the device now. And yeah, wonderful. We already see the signal, but let's first go to the modulator. And what we see is select waveform. So this is the waveform we just created. It's 360 samples, and amazing enough, we get like the right signal with 300 something samples or so. We got here some of the data that we can still change about it. And in the overall menu, we can do the triggering stuff. We can do clock frequency changes, and of course we can do the modulation and the level as with any device. And look at here, we perfectly got like the waveform that we're looking at. Huh? So we got a bit of a noisy signal still here, but when I will basically choose to have everything out the signal, let me get the cursor right out of the way. We basically got the signal exactly as we would have expected it, with one carrier at 100 megahertz. I think it was slightly below if we looked at the specifications that we did, the 2 carriers over here and the 3 carriers over there. And if you will be interested to know the spacing between the carriers here, how we could be using the cursor function of the device. Actually, I already moved them in the right position, and we see that the spacing between the cursors here, is 1.05 megahertz. So yeah, that's exactly the type of spacing that we had programmed. So yeah, fantastic. This software, this device, all 20 years old, can still generate all this type of complex multi-carrier signals without any problem. So I'm very happy about this. Okay, now we're entering in part 2 of the videos. How did I get this working? Because that was something that was quite a bit of a challenge and kept me quite a couple of weeks trying to do different types of things. So what is the point really? We're talking here about a piece of software that is needed to talk to the SMIQ, which is written also some 20-25 years ago, and basically we have to rebuild the whole computer environment as if it would have looked like 25 years ago. And I can take you in a couple of steps what I did, and also especially where I failed to do something and I needed to take other steps. So let's go and take a look at it. Well, first of all, WinIQSIM basically needs a version of Windows that's kind of regular in the time that this program was being released. And I think the earliest version of WinIQ go back to 2002. The very last version that I'm using here, 4.4, is from halfway 2006. And that was the era of Windows XP. Vista, I'll stay away from Vista, and we might try Windows 7. I can already tell you that it's simply not working under modern Windows version. You get a lot of errors with installing it, and I didn't get it to work properly. So I have to go back in time and build a computer basically with this older type of operating system. Now the next challenge basically there is build this computer with an other operating system and get it to talk to the device. And so we got the professional GPIB interface, and that was my first choice, of course. And I've been trying to use the rather popular, I think, Agilent USB to GPIB interface by installing the software suite on that. And I took the software suite that is still supported or still supporting Windows XT, and that's the 17 version of the Keysight suite. So install that whole thing, and basically that seems to run nicely. It recognizes device. We see everything there as we would expect it to do. But then it needs to talk as well to the Rohde and Schwarz software. And Rohde and Schwarz, apparently for this particular program, it really expects the National Instrument Visa library and not another one like the one of Keysight. So the step that you should be taking then, I think, is also install the National Instrument Library. And here you see the library version as it existed or was supported at the time of Windows XT. And then on top of it, you can go to your Keysight part, and there you can configure that it kind of links up to that other library, and it allows you to use legacy devices on the National Instrument visa. So that is activated, and you also see then that the Keysight visa is the secondary implementation running, and the first implementation is then the one of National Instruments. But then we got to test it a bit, and as long as we're basically testing in the Keysight Agilent environment, everything runs well. How you see the device is well recognized, but I can also run basically an I/O monitor. I see the communication going up and down to my device, and so when I ask the device for the identity, then as you see on the screen, the I/O monitor nicely shows what communication is going up and down. Unfortunately, when I'm trying to run the Rohde and Schwarz software, it basically doesn't work. There's no traffic going on. I don't see anything happening in the I/O monitor as well. Funny enough, when I activate this compatibility mode with National Instrument, something is happening because I do hear some clicks and some relays in my Rohde and Schwarz, and apparently there is some communications going on, which was not there before I started this compatibility mode, but in the end it's not working and not anything I'm seeing in the I/O monitor. I tried a lot and eventually never get it going. So I decided to look for another route, and basically that other route is trying to use a serial interface, which I think is kind of your second option here. And well, the serial interface I'm using is pretty straightforward. This is called by a company called Deloc. I think it's Belgium actually, and they got these nice simple interfaces that bring basically USB 2 to a serial interface. But also there I had to go through a couple of steps to get this working. Because it's not completely trivial. It's easy to do on a recent operating system, but I had to get back to Windows XT, and the Windows XT support basically was not available by the maker of this cable, but in the end I figured out what chipset is there, and I found in some old archives some chipset drivers at the early 2000s or so. But then note there are two different drivers. There's the D2XX drivers and there's the VCP driver. And initially I only managed to get the D2XX driver to work, which is nice to have, but it's not generating a COM port, a serial port, and it's the COM port that you need. So you need the VCP driver, and that basically, once you have that driver, you get an additional virtual COM port added to your device, and then you can specify the parameters on that COM port, and then you can start talking to the Rohde and Schwarz program. So basically then we were almost there, unless I've been trying this a lot and I've been able to talk from my computer and get some screens and maybe send over 100 bytes, and then everything went wrong again. And at that point I couldn't figure it out further what was really happening there. And then I decided to try with some other computers as well. And so what my preliminary conclusion is here, I start building everything from a virtual machine environment. So I took a modern computer, I had a virtual machine environment running in there, and Windows XP is from there, including all the drivers, etc. And didn't get that to work, and I think in the end, maybe the virtual machine was too fast. And what do I mean by that? This software was never tested those days on computers that were a multitude of factors faster than they ever were in the time of Windows XT. And maybe there's some timing parameters or other things going on with the serial interface or the program that simply doesn't go. So eventually my solution was, I got like a real old computer that I got still from a family member that is actually from the early 2000s. That one is actually not running Windows XT but Windows 7 slightly later, but then I reinstalled everything there and all the serial drivers, etc., and then it worked flawlessly, and we can do like big files like all the way to the waveform memory of the device. So I think it was basically the speed of my virtual machine or something else, but normally I don't run into this type of issues. But anyway, the solution was to get really old hardware with it as well. Okay, that's it for now. I'm happy that I got this unit working, and I hope you like this video. And if you have an SMIQ yourself, I hope this also helps to get the arbitrary waveform function working for
for you as well. And well, see you next time at Rudy's Electronics Lab.